Hey everyone, welcome to this first video in our differential equation series. And in this video we're going to start off by introducing what a differential equation is and solving one of the easier types of differential equations. So what is a differential equation? Well, say you had some function y that depended on x. So there was some relationship between y and x. Y could be x squared, y could be sine x, could be some composite function, etc. A differential equation relates the derivative of y, so dy dx, the rate at which y changes with respect to x, to the variables y and x somehow, so it could be some other function of y and x. And that's what a differential equation is. An ordinary differential equation is one where x is the only possible variable that can influence y. So dy dx is the rate at which y changes with respect to x. There's no other variable out there that could affect the value of y. Y only depends on x. And this is a first order differential equation because the first derivative is the highest order derivative that appears in the differential equation. Great, so that's the groundwork for what a differential equation is. Let's get started by solving first order ordinary differential equations that are separable. So to understand what separable means, a first order ordinary differential equation that's separable looks like this. So dy dx is equal to some function, let's call it big X, that only depends on x, and some other function big Y that only depends on y. It's called separable because we can separate this function's relationship on x and its relationship on y, or its dependence on x and its dependence on y. They can be separated from each other, and this is a useful trick for equations like Schrodinger's equation, which is incredibly useful in quantum mechanics. So how would you go about solving this? Well, as the name suggests, we'll try to separate the x and y components. This is called the method of separation of variables, because that's exactly what we're doing here. So the main idea is to get all the x's on one side and y's on the other, and that would look like this. Now, this might be a bit hand-wavy because we've treated dy over dx as a fraction, and it's not exactly correct mathematically, but it does work if we integrate both sides. So we can't just separate the dy dx relationships without the integration on both sides. By solving that, you should be able to get your solution to your differential equation. So let's start off with a few examples. Say you have dy dx is equal to 2 minus y. That's fairly straightforward. You can get the y's on one side integrated and the x's on the other side. Integrating this, we get negative natural log of the absolute value of 2 minus y is equal to x, and we can group the integration constants from both sides together. And exponentiating both sides, we see that 2 minus y absolute value is equal to e to the minus x minus c, and we can write that out a bit more neatly by having some constant a times e to the minus x, where a is equal to e to the minus c. So c is a constant, that makes a constant. And now usually the question comes with some sort of conditions on y. So if it comes with the initial value that y0 is equal to 0, that's what we call an initial value, which serves as a sort of boundary condition that we can use for figuring out what a is. So it's just as you'd use some condition to figure out what your constant of integration is when you're doing regular old integration. In general, an nth order needs n conditions to get your exact solution. So this is the first order, we just need this one condition over here. So plugging that in, when x is 0, y is 0, so that means the absolute value of 2 minus 0 is equal to a times e to the 0, which tells us a equals 2. So we can see that the absolute value of 2 minus y is equal to 2 times e to the minus x. Notice here how this depends on 2 minus y, which is to do with how we integrate log x, because you can't have log of any negative argument being a real number. So let's just have a look at what this graph would look like if we were to plot out 2 minus y. So we start off with any value of y, we negate it, and that shouldn't have any effect on its absolute value, and then we add 2 to all of them. So the graph should look like this, that point here being 2 on the y-axis. And if we know that y is always going to be greater than 0, we can see that this graph aligns perfectly with the graph of what 2 minus y would look like. So in that case, we can actually get rid of the absolute value if we know this condition is going to happen, and most of the time the problem would say so. So that lets us simplify this equation even further, and we can say that y equals 2 minus 2e to the minus x. That's our final solution. Let's have a look at one more example that's going to be a little more involved. So say we have dy dx, so still a first order, is equal to 2x times 1 plus y squared divided by 1 plus x squared squared. So this looks nasty, but let's try solving it the way we would for any separable equation. We can separate this out into 1 over 1 plus y squared dy integrated is equal to 2x over 1 plus x squared dx integrated. The left side is actually fairly straightforward to integrate if we can spot that the derivative of arctan or inverse tan x is equal to 1 over 1 plus x squared. For the right side, we'd have to use a u substitution where u is 1 plus x squared, which tells us that du is 2x. And combining these two facts, we can rewrite that integral as the integral of 1 over u squared du. That's this over here. Amazing. So let's use both those ideas to rewrite both sides of this. So the right side just becomes arctan of y, because y is the argument and the integration variable. The left side becomes the integral of u to the minus 2, essentially, which is equal to minus u to the minus 1 plus c. So we know what u is in terms of x, so that would be minus 1 over 1 plus x squared plus c. Taking tan on both sides, we can rewrite this as y is equal to tan of minus 1 over 1 plus x squared plus c. And that's our solution. And yeah, there weren't any initial conditions to this problem, so this would be our final solution expressing y in terms of x.